Section 6.6, exponential and logarithmic equations. In this section, we're going to use like bases to solve exponential equations. We will use logarithms to solve exponential equations. We will use the definition of logarithms to solve logarithmic equations. We will use one-to-one property of logarithms to solve logarithmic equations. We will solve applied problems involving exponential equations. Here's a warm-up activity. Solve the following equations. So the first equation is basically a quadratic equation, which means we can't factor it. So we're going to use the quadratic formula. So we're going to have x equals to negative b plus or minus square root of b squared minus 4ac divided by 2a. That is 1 plus or minus square root of 1 minus 24 over 2. That is 1 plus or minus square root of negative 23 divided by 2. And that is basically 1 plus or minus square root of 23i over 2. So the solution is two complex numbers in this case. The second part, we have log base 6 of 6 raised to the 2x equals 8. So we can rewrite this as, can bring the power down. So 2x times log base 6 of 6 equals 8. We know that log base 6 of 6 is equal to 1. So this is 2x times 1 will lead to 2x equals 8. And by dividing both sides by 2, we get x equals to 4. C is a rational equation. So we're going to multiply both sides by the denominator to eliminate it. These will cancel together. And we will have x plus 2 equals 4 times x minus 1. We will distribute the 4 inside. We will get x plus 2 equals 4x minus 4. Now we're going to gather the x's together. So I'm going to subtract x from that side and that side. We will end up with 2 equals 3x minus 4. I will need to remove the 4 from here. So I'm going to add 4 to both sides. I will get 3x equals 6. Divide both sides by 3. We get x equals 2. Last but not least, we have 6 raised to the log base 6 of 8 equals 2x. So we can rewrite this as a log because it's an exponential form. We can rewrite it as the base is 6. So we're going to say log base 6 of 2x equals log base 6 of 8. So we know that log base b of x can turn into b raised, if you have y equals to, b raised to the y power equals to x. So that is what we did there. We turned the exponent into a logarithm. That is log base b of the answer equals the exponent. That is exactly what I did there. Now, I have the same bases on both sides. By comparison, I know that because those are the same logs with the same bases, the arguments are the same. So I have 2x equals 8. By comparison, if you divide both sides by 2, you get x equals 4, and that would be the final answer. So now that we know how to solve these equations and how to use the rules that we studied already, let's put it together and see if we can compute or find or solve exponential equations using what we learned so far. The first technique involves two functions with like bases, similar to what we did in the logs exactly, but with the bases. So if we have like bases, recall that the one-to-one property of exponential functions tells us that for any real numbers b, x, and y, where b is positive and b is not equal to 1, we know that b to the x is equal to b to the y power if and only if x is equal to y. That means if the bases are the same, we can conclude that the exponents have to be the same because of the one-to-one property of exponential functions. In other words, when an exponential equation has the same base on each side, the exponents must be equal. That is the property we're using here. This also applies when the exponents are algebraic expressions. Therefore, we can solve many exponential equations by using the rules of exponents to rewrite each side as a power with the same base. So if we strive to make both bases the same, we will be able to solve many exponential equations, not all exponential equations though. So let's try some examples here. The first expression, we have 3 to the x power equals 81. So I know that I can rewrite the equation 3 to the x power equals 2. I can rewrite 81 as 3 to the 4th power. Again, with the one-to-one property of exponents, similar to the one-to-one property that I used for the logs here. We're going to say that because the bases are the same, then the exponents are going to be the same as well. So by comparison of the exponents, I know that x is equal to 4. Same with part B. Part B, as you can see here, we have the same bases ready. So we can say and we can conclude that the first exponent, x plus 4, is the same as 2x minus 2. And then we can solve that expression. First, we're going to add 2 to both sides of the equation. We get x plus 6 equals 2x. And then I'm going to subtract x from both sides of the equation. So I will have x equals 6. And that is the final answer. For part C, I can rewrite the expression as 2 to the x plus 4 equals, and I know that I can write 8 as 2 to the 3rd power times 2x minus 2 because the power of the power multiplies. And now I can conclude that x plus 4 is the same as 3 times 2x minus 2. And then after solving that, I will end up with x equals to 2. So after you solve the expression or solve the equation, you will get x is equal to 2. Last but not least, I have 3 to the 5 raised to the 5x times 9 raised to the x squared equals 27. I'm going to write rewrite the left-hand side, so 3 to the 5x times, I know that I can write 9 as 3 to the 2nd power. So 3 to the 2nd power times x squared, and then the right-hand side is going to be 27. Now, I know from what we did previously that I can combine the multiplication of the exponential expressions on the left by combining the exponents by addition. So this is going to combine into 3 to the 5x plus 2x squared, and then the right-hand side can be written as 3 to the 3rd power. 27 is 3 to the 3rd power. Now, I know by the one-to-one property of exponents that 5x plus 2x squared equals to 3. If you solve that, you will get two solutions, either x equals 0.5 or x equals -3. So we're going to use the quadratic equation for that, by the way. We're going to use the quadratic formula to solve the last one. With the same property we used for the exponential functions, we're going to solve exponential equations using logarithms. Sometimes the terms of an exponential equation cannot be rewritten with a common base. It happens a lot, so we cannot compare the bases and make the exponents equal to one another. In these cases, we solve by taking the logarithm of each side. Recall that since log A is equal to log B is equivalent to A equals to B, which is the property that I used for D here to solve it, this one right here. Okay. We may apply logarithms with the same base on both sides of an exponential equation. This allows us to take the logarithm of both sides, bringing down the power. So the power of logarithm is being able to bring any power down, and that is mostly what we need to solve exponential equations. Here is an example. If you have 3 to the x power is equal to 9, we know that x is equal to 2, because we know if we raise 3 to the second power, the answer is 9. Similar to that, if you have 3 to the x power is equal to 27, because we can rewrite 27 as 3 to the third power, and we use the one-to-one property for exponents, we can conclude that x is equal to 3. However, if you have 3 to the x power is equal to 18, what is the answer here? What is the value for x? So we cannot turn 18 into a base of 3. 3 raised to what power is equal to 18? We cannot determine that. So what we're going to do, we're going to take the log of both sides. Sometimes we use the common log. Sometimes we use the natural logarithm, which is the most common method to use. Instead of using the common logarithm, we use the natural logarithm. However, both should lead to the same answer. Both should lead to the same answer. So when we do that, we know that the logarithm is going to bring the power down. So that is exactly what happened here, equals log 18. Now, log 3 is a number. So we're going to divide both sides by that number in order to solve for x. And that is exactly what we get here. And you can plug this into the calculator and find out the answer, which is going to be 2.63. Let's try some of these questions. So we have 4 to the x power is equal to 17. Again, we cannot convert 17 into a base of 4 raised to some power. So we're going to take the natural logarithm for both sides. Again, you can take the common logarithm or the natural logarithm. So we're going to take the natural logarithm of 4 to the x power equals to the natural logarithm of 17. The power is going to come down. So what we have here, we will have x natural logarithm of 4 equals natural logarithm of 17. Natural logarithm of 4 is a number, so we're going to divide by that, both sides of the equation. So we will have x equals to natural logarithm of 17 divided by natural logarithm of 4. If you compute that, you'll get approximately, you can leave it like that. You don't have to find the final answer. So you can leave the answer like that. These are numbers. You can plug them into the calculator to find the final answer, or you can just leave it like this. Part B, same thing here. So, since we can't write 20 as 10, base 10 raised to any power, we're going to take the natural logarithm for both sides. So we're going to take natural logarithm of 10 to the x power equals natural logarithm of 20. Again, the power is going to come down, so becomes x natural logarithm of 10 equals natural logarithm of 20. Divide by natural logarithm of 10. Both sides, we get x equals natural logarithm of 10 divided by natural logarithm of 20 divided by natural logarithm of 10. C, we're going to take the natural logarithm for both sides. So natural logarithm of e to the negative 0.4t equals natural logarithm of 0.5. I know that from previous work, the fact that ln is going to cancel e, and the power is going to come down anyways. So ln of e is equal to 1. So this is going to be negative 0.4t equals natural logarithm of 0.5. Divide both sides by negative 0.4. So t equals natural logarithm of 1/2 divided by negative 0.5. That is the final answer. Last but not least, we're going to take the natural logarithm for both sides. So natural logarithm of 5 raised to the x minus 2 equals natural logarithm of 4 to the x power. The power is going to come down. The power is going to come down. So we will have x minus 2 natural logarithm of 5 equals x natural logarithm of 4. What do we do here? So we're going to first distribute the natural logarithm of 5. And we're going to have x natural logarithm of 5 minus 2 natural logarithm of 5 equals. So now we gather all of the x terms together, which is this term and that term. And then we have to remove the term that doesn't have an x to the other side. So I'll subtract x natural logarithm of 4 from both sides. I will get x natural logarithm of 5 minus x natural logarithm of 4 minus 2 natural logarithm of 5 equals 0. Now you will need to add 2 natural logarithm of 5 to both sides of the equation. So you will have x natural logarithm of 5 minus x natural logarithm of 4 equals 2 natural logarithm of 5. Now, I will take x out as a common factor. So I will have x natural logarithm of 5 minus natural logarithm of 4 equals 2 natural logarithm of 5. Now I'm going to divide both sides by natural logarithm of 5 minus natural logarithm of 4. Same on the other side. I will end up with x equals to 2 natural logarithm of 5 divided by natural logarithm of 5 minus natural logarithm of 4. Now that we have that, we can basically say that is the answer, and we can leave it like this, or we can find the answer using the calculator. So when we solve logarithmic equations, here are the steps that we need to follow. The first step is to try to obtain a single logarithm term on one side of the equation and any numbers on the other side of the equation. And then we're going to change from logarithmic form to an exponential form to solve. If there are no numbers on any side, try to obtain a single logarithm equation on either side, which means we're going to have log on each side, and that will lead to the arguments being equal. So we can basically say if we have two logs that are equal, that will lead to the arguments being equal. So it's either the first case or the second case. And then we're going to check the solutions. Sometimes we will obtain more than one solution and only one solution would work. Sometimes none of the solutions would work. So let's try these methods. So the first one, we have log base 10, because the base is not written, so that's a common logarithm, of 10x minus 2 equals log 7 minus 4x, which means we have log on either side of the equation. We can basically say the arguments are the same, so 10x minus 2 is equal to 7 minus 4x, and then we're going to solve regularly. So we'll have 10x plus 4x equals 7 plus 2. I'm doing multiple steps at a time. So we have 14x equals 9. Divide by 14 both sides of the equation. We get x is equal to 9 over 14. And as you can see, this solution is not going to cause any trouble, whether you plug it in the first or the second logarithm. So that is the solution in this case. For part B, notice how on the left side we have two logarithms. So we need to condense these logarithms into one logarithm. I notice there's a minus sign in between them. So that means I'm going to use the quotient rule, which is going to turn the left-hand side into logarithm of x plus 10 over x plus 4 equals logarithm of x. Now, I have log on each side of the equation, which means I can consider the arguments are the same. So I can say x plus 10 over x plus 4 is equal to x. I'm going to multiply both sides by x plus 4 to eliminate the denominator. These will cancel, and I will have x plus 10 equals 2. I'm going to distribute the x inside. X squared plus 4x. Now that is quadratic, so I need one side to be 0. I'm going to subtract x and 10 from both sides. So I will end up with x squared plus 3x minus 10 equals 0. And then I will solve that quadratic equation. I'm going to try to factor. I need two numbers. The product is negative 10. Their sum is 3. That is positive 5 and negative 2. So the solutions are x equals to 2 and x equals to negative 5. Notice how negative 5 does not work because logarithms cannot take negative numbers. If I plug it in here, it's not going to work out. And that doesn't work either. So I'm going to eliminate one answer and then stick to just x is equal to 2, which is not going to cause any trouble. So the solution is x is equal to 2. Part C, I need to remove the log. So I'm going to use the first method here. So I'm going to try to obtain a single logarithm on one side and kick any number to the other side. So the first step here is to subtract 5 from both sides of the equation. I will have log base 6 of 3x equals 7 minus 5 is 2. And now I'm going to turn that into an exponential form, same step. So I'm going to say I have 6 raised to the second power equals 3x, which means 36 equals 3x, which means if I divide both sides by 3, I will get x is equal to 12. That is the answer. For part D, I will have 2 logarithms on the left-hand side, which means I need to condense this into one logarithm. That is case number 2. So I'm just going to say log base 3 of x minus 5. I see addition, so it's going to be a product of arguments equals 2. Now, I'm going to turn this into an exponential form, so I know that 3 to the second power is equal to the argument. So now I need to expand that expression and then make this into a quadratic with the left side or the left-hand side is equal to 0. So this is going to be x squared minus 5x plus 3x is minus 2x, and then minus 15 equals 9. 3 squared is equal to 9. Now I need to remove the 9 from here because this is quadratic, so I need the right-hand side to be 0. I will end up with x squared minus 2x minus 24 equals to 0, and then I will factor. I have x and x. I need two numbers. The product is 24, negative 24, and the difference is negative 2. That is negative 6 and positive 4. So the answer is going to be x is either negative 4 or x is equal to 6. Let's see which one is going to work and which one is not going to work out. If I choose negative 4, I notice that it's not going to work for this expression right here. It's going to have a negative argument. That doesn't work. Negative argument here as well, so that solution is not going to work. So I will eliminate that solution, and the only solution I have is x is equal to 6. Last but not least, let's try natural logarithm of x is equal to 2. So first I'm going to turn this into an exponential form. I have a log on this side. So I'm going to say this is equal to the base e raised to the second power equals to natural logarithm of x. So that is one step. And then I will do it again because I have a natural logarithm on one side. So I'm going to repeat the step one more time. So I'm just going to say, well, that is base, which is e in this case, raised to the e to the second power is equal to x. And that should be the solution. That should be the solution. You can find out the answer by using the calculator, or you can leave it like that because that is basically a number. Last but not least, we're going to do a problem involving application. Example, the population growth of a city is modeled with the following formula. A of t is equal to 234,000 e to the 0.0046t, where the initial population is 234,000 and t is in years. How long will it take for the population to grow to 245,000? In order to find the answer, I know what I have here. I have the final population is 245,000, and I know the initial population and I know the rest, so I'm just going to substitute a into my equation. So 245,000 equals 234,000 e to the 0.0046t, and I need to solve for t. The first step here is to divide both sides by 234,000. If you do that, these are going to cancel out. And then the division, so that is going to be 245. These zeros are going to cancel, divided by 234. I'm going to leave it as a fraction. Equals to e to the 0.0046t. Now, I need to remove the e, so I'm just going to take the natural logarithm for both sides of the equation. What this does, I know that the natural logarithm is going to bring the power of the exponent down. So it's going to be 0.0046, I'm starting with this side, times natural logarithm of e. I know that the natural logarithm of e is equal to 1 equals to the natural logarithm of 245 divided by 234. I just flipped the sides, so I began with what I know first. Now, because this is gonna cancel out and it's going to be 1, I will have on this side, I forgot the t by the way, so 0.0046t, which was the exponent, equals to natural logarithm of 245 divided by 234. I'm going to divide both sides by 0.0046 to solve for t. And if you do the division, you will end up with t is approximately equal to, if you plug that into your calculator, you will get approximately 10 years. So it'll take 10 years for the population to grow from 234,000 to 245,000 at that rate given in the equation. That is the end of section 6.6. If you have any questions from any section, please let me know.